My name's Ian Flint. This is Varun Varma, and we work at Oath, a company formerly known as Yahoo and AOL and Edgecast. So we were all combined as part of the acquisition of Yahoo by Verizon. And I run network automation. One of the big challenges that I faced when I came onto the team was the proliferation of point solutions for doing monitoring of devices. And so we had a whole bunch of them. We have a significant MRTG footprint that's hitting our devices. We have a custom SNMP puller called YWatch that's hitting our devices. We have a point solution around load balancers, just all of these systems that had grown up organically over the years, and the systems that depended on them that had also grown up around them. And so one of the challenges that we undertook to solve was to take those and consolidate them into a single polling platform, a universal polling and metrics distribution platform, which we called Panoptes. That's what we're going to be talking about today. So,
hi, my name's Varun. I'm the lead engineer for Panoptes. And as Ian had mentioned, so essentially we built Panoptes as a Python-based network telemetry platform. There are three distinct components that Panoptes has. There's discovery, polling, and enrichment. And we'll be talking about some of these details during this talk. Here is an overview architecture diagram of what Panoptes looks like. So it's based on some supporting services. There is Celery, which is a very popular Python distributed job management system. There's Redis, which is an extremely fast in-memory key-value data store. There's Zookeeper that provides distributed locking and leader election services like that. And then, of course, there's Kafka, for which we use as a message bus. On top of all of this, we actually built a plugin framework, and I'll go into some of the details later. Now, we implement three types of plugins: discovery, polling, enrichment. And then on top of this entire framework, or the stack, we implement device-specific plugins. Currently, we have plugins that use SNMP and APIs to actually collect telemetry data. There's a bunch of supporting services in addition to the core platform, because obviously after we collect this entire data, we have to store this and analyze it. So we have a time series database that we use. We have an internal CMDB that we use for device discovery. And then we use Chef for deployment and configuration. I'm going to go through some of the core concepts that Panoptes as a platform has. So the very first concept is this notion of plugins. And this is where Panoptes is actually fundamentally different from a lot of SNMP-based polling solutions. So what a plugin is essentially an implementation of a well-defined Python interface class. So you can essentially, because it's Python code, you can actually write code to collect from any source that you like. It could be SNMP, could be API, CLI, or anything else that might come up in the future. As I'd mentioned, there are three types of plugins: discovery, enrichment, and metric plugins. Another core concept in Panoptes is this notion of resources. So what a resource is it's essentially an abstraction of what should be monitored. In the most common case, a device or a network device or a host is a resource. But a resource could be an external API endpoint. There's metadata associated with resources. Another interesting thing in Panoptes is that we've come up with a DSL, which actually mirrors or is quite close to SQL, which lets you actually select resources. You can see an example of the DSL on the screen, where we're saying, okay, I want you to apply certain type of polling only to devices which match this criteria. Now, typically, these types of DSLs are available within time series databases on analytic tools. But here, the difference is that we actually have made it available even at the time of deciding what to poll and how to poll it. Another concept is metrics, which obviously is one of the core things. A metric is anything that can be measured. So it's essentially always a number. Metrics typically tend to be fast changing. While that might sound obvious, I'm going to contrast it with something called enrichments later on. And like I said, because of the plugin architecture, metrics can actually be collected through any mechanism. Okay? Another concept that we have introduced is the notion of enrichments. Now, what enrichments are things that are not numbers. They could be numbers, but essentially these are things which are not that frequently changing. A perfect example would be when we're collecting telemetry data for interface metrics, right? So the interface counters are metrics, but the interface name is actually an enrichment that we apply. And the thing is, and enrichments might not necessarily just come from the device that's being monitored, it might come from external systems. One example is when we poll a device for, say, BGP sessions, we get back ASN numbers. Now, we might be interested in reporting the actual peer name, not just the ASN number. And that's where, that's not something we can query from the device itself. So that's again a place where the enrichment framework comes in, where we can query and enhance the data that we've collected from the device by using external lookups. Also, because metrics are typically not numbers, they're typically strings, they tend to be more expensive to process than metrics. And that's one of the reasons there's transformation and lookups needed. Case in point, for example, I mentioned the ASN number to name lookup. It's not something you want to do on every poll cycle. It's also something that, because they're expensive, we tend to cache them. Again, an example is interface names, interface aliases, things like this, which we don't actually need to collect in every poll cycle. Overall, what this does is, by being able to divide metrics and enrichments, is it actually lets us scale a lot, because we don't have to collect the complete set of data on every poll cycle. Now, a word about the data encoding and distribution. Panoptes was built from day one as a distributed system. We knew that at our scale, building a system which could only scale vertically, which means we had to add more processors or more memory to the same host, would simply not work. So we've actually built it as a horizontally scalable system. And there are two dimensions to that. One is the fact that the three subsystems that I mentioned, discovery, enrichment, and polling, are completely decoupled. Which means we can scale them out individually. It also means that within each of these systems, we can actually spin up more hosts. And for example, if I need more polling capacity, I can simply spin up more hosts, and it becomes part of a cluster, and I get more polling capacity. Because these systems because it's a distributed system, we obviously need a way to pass data between them. We use Kafka and Redis, depending on different use cases, to actually pass data between these subsystems. The other thing is, again, because we're passing data, we need to choose a serialization format. So we decided to go with JSON. Now, JSON is extremely inefficient and it's slow, but then it is actually very operator and developer friendly. So it's a cost we were willing to pay. This is what the overall workflow for this looks like. So, obviously, it begins by us collecting data. There is some post-processing support that we have. We call these transformations. An example of a transformation is that when we collect raw counters from a device, sometimes it's not meaningful to send it as is downstream. So we can actually convert them into gauges. And then once we do the post-processing, we place the data on the message bus. And then we have different consumers. Here are two workflows that I've shown. There's one workflow that takes the data and puts it in a time series database, which we actually use for graphing, alerting, and our internal time series database actually also stores the data on our internal grid, which we use for analytics and reporting. At the same time, there are use cases where we need the most recent data, not necessarily the historical data. So we actually have a consumer which stores this data in MySQL and exposes this through an API. And then we built UIs and CLIs based on top of those APIs, and I'll be showing an example of what that looks like. So given that we serve 1 billion plus customers, obviously we have a very large footprint. And there are a lot of things that we learned while operating this. First, let's talk about what the scale we're operating at is. Now, this is an indication of orders of magnitude. These are not absolute numbers. So we have hundreds of thousands of servers. We have tens of thousands of network devices. We have millions of time series. We do collect data every 60 seconds, which is actually faster than typically what we were doing with MRTG of every 5 minutes. Now, some of the scaling issues we faced. I mentioned earlier that Panoptes was designed to be horizontally scalable, and this was intentional. We paid a lot of upfront development cost to do this because, frankly, this is not easy to bolt on. Scalability is not a feature. It's a design principle, so you kind of have to take care of it while designing the system. We decided to go with Python. It is extremely slow, extremely inefficient, something we were prepared for, and it turned out to be true. What we have done is there are some high throughput actions, like specifically the actual SNMP protocol interactions, we've delegated to C extension modules so that we can actually get performance. And then again, at our scale, we broke everything. All the default installs for Redis, Zookeeper, Kafka, they would just fall over because we would hit all the default limits. So there's a lot of tuning we had to do for each of these systems. The other aspect for scaling was with data this large, we did not want to build a centralized system, both for performance and availability reasons. So the way we did this instead was that we have these local deployments in each of our data centers. And what we do is these data centers collect data for their, obviously, all the network devices within the data center, but also collect devices for nearby regional sites. At the same time, we don't want discovery of data to be problematic. So somebody using an API should not have to figure out where they can get this data. So what we did was we came up with a federated API structure where what we do is between all these data centers, we actually cross-populate the metadata. So each data center does not have all the data, but it knows where to get all the data. So you can make a query and say, okay, I'm interested in data about device X. And you might get a response saying, here's the data. Or you might get a response saying, okay, I don't have the data, but I know who does, so why don't you go ask that person? And this design has helped us both with scalability and fault tolerance. The plugins that we have already written, we have support for Arista, Cisco Juniper metrics, we have system metrics, we have something we called functional metrics, which is go beyond just the CPU memory, and they're very, very device and platform specific, and more importantly, they're usage specific. So if you're using an A10 load balancer for load balancing, we have different functional metrics versus when we use it for large-scale NATs. What we've also done is, because this is a platform for telemetry collection, we've actually also built state and topology collection for Cisco devices. This is something we're looking at actually integrating back into our discovery so that we don't only figure out what devices to monitor through our CMDB, but through an actual walk of the network. Some operational experiences that we've had, and anybody who's worked with network telemetry, I'm sure, would have seen these. We had a lot of inconsistencies between metrics which were reported from different platforms and different OS versions of the same platform. And frankly, in terms of development, this was our single biggest time drain. SNMP, it is really old. I believe the SNMP v2 specification came out 21 years ago. So it is old, but it is ubiquitous. As much as we'd like to be able to use API and streaming telemetry, there just simply are many cases where a lot of telemetry data is not exposed through those. So, it's something we have to live with. API performance tends to be much better than SNMP. Again, anybody who's done telemetry would know this. The other thing is, when we were building this, we had some use cases. Like Ian had mentioned that there was a whole class of services or systems that we had, and we knew what we wanted to replace. But we also knew we didn't know how this data would be used. And that's where, for example, using Kafka proved to be the right choice. We already have 3 types of downstream consumers which transform the data and send it to different systems. And this is a much better approach than trying to collect data the same data in different ways so different downstream systems can consume it. I'm sorry, I think the slide's been repeated. Oh, sorry, I'm going back. One interesting thing is, one thing we were very careful about is, even though we place all our data on Kafka, we do not integrate those raw streams with third-party systems. Now, this might sound counterintuitive because one of the big advantages of using Kafka is there are so many consumers that you should be able to hook in any consumer and get the data. But here's the problem. If you do that, you can never upgrade. Because the problem you will have is you'll be tied into a certain Kafka version because there's a downstream consumer that depends on that Kafka version. Or you'll be tied into a specific serialization format, whatever you were exposing on sending or serializing with on Kafka. If you ever change that, your downstream consumers will break. What we do instead is that we actually take this data and we store it in a transient MySQL database and expose APIs. And I'm going to show an example of the APIs we have. And the advantage that has is it completely decouples my system. We can change the internal serialization. Heck, we can even get rid of Kafka for something else that comes along without our external contracts changing. We built custom UIs. Again, I'll show a couple of examples of what that looks like. These are examples of APIs that we have. On the left, you would see this is a very purpose-specific API that we've built to get data for whips from load balancers. At the same time, and this tends to be very easy to use and performant. We also only expose the last data point through the API. We also have a API which actually exposes historical data, and you can do ad hoc queries on it. This is actually an OpenTSDB API. So this is not something we've built. Internally, we use OpenTSDB. Tends to be slower, but then you can run aggregations and you can get historical data. One of the things I mentioned in the architecture slide is that we have a time series database. So we actually have an in-house time series database and visualization solutions, which Ian actually had architected. It's based on OpenTSDB with a lot of, obviously, performance optimizations, a lot of other improvements. This is an example of a dashboard that we've built based on our internal TSDB and the internal UI that we have. Now, because it's a centralized TSDB, our team doesn't have to manage it. It's managed by a central team for the whole of Oath, and there's economies of scale and operations are simpler. Here's an example of a couple of custom UIs that we've built. The left-hand side is actually a device dashboard. The right-hand side is actually a WIP dashboard. Now, these have been built using the purpose-specific APIs that I had shown. And because they only expose the last point-in-time data, they tend to be performant, so our UIs are actually quite responsive. Looking forward, one of the next things that we want to work on is actually streaming telemetry. We have framework in mind where we use a streaming telemetry collection. gNMI is the leading contender. But we also reuse the infrastructure that as we have. For example, in the gNMI case, we do need to create outbound connections to actually get streaming telemetry from them. And for that, you need an authoritative source of devices or resources to connect to. That's something Panoptes has. Similarly, for gNMI, you would want to, the raw metrics or telemetry data that you get over streaming, you will again want to enrich them. Examples of enrichment, I gave the ASN example, but there's another example. For example, the geolocation, the physical geolocation of the device is not necessarily something that you can figure out from the device itself. So these are external enrichments that we can apply to the raw metrics that we collect. Now, we've actually spoken and presented a lot of this at NANOG 70. So the big thing, though, is the stuff that we've done after that. When we presented it at NANOG 70, we had discovery and polling. We did not have enrichment. What that meant was that on every poll cycle, we would actually be getting all the static information again, which had scalability problems both for the platform as well as for the network devices. By adding an enrichment subsystem, we have alleviated those concerns. We have implemented we actually have implemented a whole bunch of plugins to give us full coverage or close to full coverage with a network which is a multi-generational, multi-vendor network like ours. We worked out scaling issues. Obviously, that required a lot of platform changes and tuning and things like that. But most importantly, what we wanted to talk to you about is that today we are actually announcing the open sourcing of Panoptes. We are releasing an MVP. We're open sourcing the core platform that includes the 3 subsystems that I've been talking about. We are open sourcing interface metrics and enrichment plugins. This is a very small subset of the plugins we have, but in the spirit of releasing an MVP, this is what we'll be going to market with. And we're also introducing an integration with InfluxDB as a time series database. So this is an example of an InfluxDB dashboard that you can create if you actually use the open source time series, the open source implementation that Panoptes has. And you can actually go get it at this URL. Any questions?
Hi, Tony Tauber, Comcast. It looks like very good stuff, and set up the way I would think too. Also, with the enrichment cache, do you actually put the enrichment data in with the? You wouldn't put it in the time series. I mean, it wouldn't sit on the side, and you join it when you need it or something.
Okay. So the stitching happens actually at the time of polling. The polling plugin can actually choose to go out and get data from the device or actually use the data from the cache. So, but what happens is when the polling plugin is done, what comes out of this is a consistent model. Actually, I forgot, I didn't really touch upon that. We actually have well-defined internal models for everything. So, for example, taking the example of interfaces, when we collect interface metrics, no matter what platform, what version, what we're collecting interface metrics from, every plugin must produce interface metrics which has a certain set of metrics and a certain set of dimensions or tags. And those dimensions or tags could either come from the device or come from the enrichment cache. Does that make sense?
Okay, but I mean, it seems like extra if you're storing at every metric timestamp, all this metadata in the same place, that's kind of redundant because it's always the same or the same for days on end. Or
that is true, but most time series databases actually optimize that.
Oh yeah, right. Okay.
Yeah,
so they do it.
So
okay.
we count on essentially that. Yes.
Okay.
Well, and
Thanks.
oftentimes the enrichments change over time as well.
Right,
So-
they do.
So you
It's
do want to
possible.
store it with the source data so that if you do aggregations based on those, that you get an accurate answer.
Yeah, okay. Yeah, that's a good point. Makes sense. Thanks.
Hi, Aditya from Arista. Quick question on how granular is the timestamps on the time series graph? Is it millisecond granularity, 1 second?
We are collecting, so plugins, okay, because it's polling, it's not going to be accurate. It is going to be the time when the data made it to the polling collection system. The plugin is configurable. There's a parameter called execute frequency, so as frequently as you wanted to collect the data. Currently, in our production system, we have set it to collect to every 60 seconds.
Okay.
We could go down more for some devices, Arista devices, sure, but some of the other platforms, they just won't be able to handle the SNMP load.
Okay, thank you.
Which is why streaming telemetry has to come in.
I believe our backend supports 1 second resolution.
Yes.
But we poll currently at 60 second.
Also, just an implementation detail, the timestamp resolution is millisecond. Like, yeah, that's what the platform is capable of. Any other questions? Thanks, guys. Bye.